Using the drive, we can control the speed of the motor, the torque, and the direction. A typical VFD is really made up of three key components: a rectifier section, which takes the building wire 60 Hz AC and transforms it into DC. A filter section, which is basically a capacitor bank and probably an inductor bank, which smooths out all the pulses to make a true clean DC power source. After that, the DC rails are actually transformed into a pulse width modulated waveform, something like what is seen at the lower right of the screen. This is done using a sophisticated switching technology and typically microcontrollers. Typical applications for these type of drives, variable frequency drives, are material processing and handling. This, for industrial applications, would be wood processing, the automotive industry, pulp, paper, and printing, food and beverage plants, power plants, mining, metal industry, machine shops, plastics, and textile plants. Non-industrial would include water and sewage treatment plants, heating, ventilation, and air conditioning. Believe it or not, in many homes today, we use VFDs. VFD manufacturers include ABB, Rockwell Automation, Allen Bradley, Emerson, Hitachi, Toshiba, Schneider, Eaton, Baldor, Yaskawa. So a few advantages and complications. Let's look at the advantages first. One key advantage is lower maintenance cost. There's fewer mechanical components, fewer components in general, so the maintenance costs are going to be much lower. You can increase productivity. Now you can change the speed of your line or of the system to match your output rather than either turn it on or off. Fans are a very good example of this. HVAC systems. There's energy savings to be had from this as well. You can now run the motor continuously at a desired speed to make sure that whatever you're processing or moving is moving continuously at the desired speed rather than turning it on and off. You can make for smoother start and stops. You can slowly ramp the speed up. In the paper industry, this can be critical. If you turn on some of the paper manufacturing lines from a stop to a start full speed, the process doesn't work. You need that variable frequency drive or that variable speed technology. You can also, as a result of all this, produce higher quality product. Complications from using VFD systems. So because we're feeding, instead of a 60 Hz sine wave down the cable to the motor, we're feeding a pulse width modulated waveform, which typically has a carrier frequency of 2 to 4 kilohertz. We can see frequencies into the megahertz range on the power conductors of the cable. If this is allowed to leak out of the cable, you could interfere other wireless and wired systems in the building or remote to the building. There's repetitive high voltage spikes. So on a typical VFD, we can expect 3.1 times nominal voltage in spikes. So for a 600 volt rated VFD, we'll see spikes of 1.9 kV. And that's very much normal. Corona discharge is also a concern. The reflected wave and standing waves traveling up and down the cables. Possibility of motor bearing failures. And this is a result of that reflected wave and the high frequency currents. We'll see more on that in a minute. We can also see the fact that if we don't use a proper VFD cable, we'll be very much limited in cable length. Capacitance becomes a big issue. So in using a VFD cable, we significantly reduce or eliminate these complications or issues. That's why we need to focus on using a VFD cable for VFD applications. Back in the mid-90s, an IEEE study was done on VFD cables by a group of ABB engineers. In that study, there were 5 key performance concerns that were addressed. The 5 key concerns were minimizing net injected ground current into the drive system ground bus, minimizing common mode currents, minimizing motor frame standing voltage, producing the best possible cable shielding, and the best possible ground path in the cable. The result of all this is an efficient and safe system that will operate properly without interference or interaction with other systems. On the right is a picture of a bearing race that has been pitted as a result of bearing currents. These bearing currents can be eliminated or dramatically reduced if these 5 key concerns are considered. So, common question is, what are bearing currents? Well, if we look at how a VFD is connected to a motor, we'll see that we have the VFD, the motor cable being the VFD cable in this case, with the phase conductors connected from the output of the VFD to the input of the motor. That pulse width modulated waveform, that very high frequency waveform, is sent down the phase conductors or the power conductors to the motor. The motor is going to turn the rotor shaft, so the shaft of the motor, at a speed based on the fundamental frequency or the base frequency of that pulse width modulated waveform. So 50 hertz, 60 hertz, 20 hertz, whatever it may be. Everything else to the motor is seen as garbage and noise. It wants to return it back to the drive, back to the VFD. If the cable is a sufficiently low impedance for low frequency and high frequency currents, then the cable is going to be the return path. So in the case of a VFD cable, that's what it's designed for. Now, if you're to use a non-VFD cable, such as a tech cable, even though it has aluminum interlock armor, it's not a very good high frequency bond path. So what's going to happen in that case is you're going to get these high frequency currents circulating throughout the motor. So circulating through the shaft of the motor, jump through the bearings to the housing, back through the bearings at the other end, back into the shaft and circulate through. It could also escape the motor through the shaft of the motor, through the driven machinery, and also cause this current to electrical discharge machine the bearings in the driven machinery as well, and return back through building steel or plumbing. You would think this might be okay, but the problem there is that the building steel, the plumbing, whatever, may be an antenna. It may actually radiate that high frequency noise out. And there have been documented cases of local AM radio stations having issues broadcasting when VFDs are running, if the frequencies happen to line up. So it's not only your systems within your building that could be affected, it could be other systems, other buildings. So a couple quick little facts here, just to break things up. VFDs have been used in HVAC systems in buildings for more than 40 years. So it's a very much an old technology for buildings, a very mature technology. About 5% of all motors are controlled by VFDs. I'm pretty sure that number is much higher in a paper plant. Sales of VFD technology is growing at a rate of more than 5% per year. So why use VFD cables? In an ABB document, they have a chart of transfer impedances for various types of cable. So the idea here is shielding effectiveness, or how effectively does that cable carry high frequency currents from one end to the other, and how well will it absorb and sink those high frequency currents if they escape from the power conductors. So the threshold of 100 milliohm per meters was set up as a go, no go threshold. Anything below that is great, anything above is not desirable. Now you'd want to stay below that threshold for up into the megahertz frequency range, up into the about 100 megahertz frequency range, ideally, for a typical VFD. So if we look at that very top curve, that curve labeled as number 1 or non-recommended cable, that would be like using a tech cable or RW90 in conduit. Even 3 RW90 conductors with 3 bond conductors pulled into EMT, it's not going to behave properly. It's not going to work very well. If we look at some of the flexible VFD cable options, such as tin copper braid, a very flexible VFD cable, it's good, but it's not great. Now, this is where the trade-off comes between flexibility and performance. If you're looking for a higher performing, a better performing VFD cable that still maintains flexibility, really we should be looking for a cable with copper tapes and concentric wires for bonding. That produces a flexible, unarmored VFD cable, maintaining a somewhat flat transfer impedance. Now, if we look at our corrugated aluminum sheath or DriveRX VFD cables, you can see very quickly that the aluminum actually drops dramatically in impedance as frequency rises. It actually becomes a much better conductor than copper, the aluminum itself. So this is where many engineers get kind of muddled up in saying, well, copper is a better conductor than aluminum. Well, not really. It depends on the frequency we're talking about. In building wire frequencies, absolutely. When it comes to a VFD, aluminum is preferred. So a couple of key characteristics of a good VFD cable design: cross-link polyethylene insulated conductors. The reason for this is that recall that we were talking about the fact that it's very common to see these voltage spikes of 3.1 times nominal voltage rating, right? So our DriveRX VFD cable is rated 1 kV for 600 volt rated VFD systems. I know somebody's thinking out there already, 1.9 kV with a 1 kV rated insulation system. Well, crosslink polyethylene nowadays especially is of such a high quality that it can maintain its integrity with these repetitive spikes of 2 to 3 times its voltage rating. So really our 1 kV VFD cable can work with these voltage spikes if they go into the 2 to 3 kV rating or kV market. So 1.9 kV repetitive spikes, no problem. 3 symmetrically placed grounding conductors with 3 insulated phase conductors. There's no need for a 4th. Motors typically don't need that 4th conductor. It has to be a perfectly symmetrical, balanced construction. Otherwise, you'll have common mode currents or zero currents, which will cause, again, bearing currents. Continuous aluminum sheath is preferred. Copper tape if you need flexibility. Braided wires if you're looking for extreme flexibility, and a compromise in VFD performance. PVC overall jacket, so an overall jacket to make sure that that high frequency return path, be it the copper tape or the aluminum sheath, is bonded only at the ends. Very quick comparison chart between the various VFD cable designs that we would offer. Looking at the aluminum sheath as the best VFD cable solution, or our DriveRX VFD cable, but flexibility is okay, it's good. Again, the braided wire being the best for flexibility, and other typical building wire, Tech 90, ACWU 90, RW 90 pulled into conduit, don't use it. So a few installation tips. Use only symmetrical 3-conductor shielded VFD cables. Now, that aluminum sheath on our cable, believe it or not, is a shield, it's an armor, and it's a high frequency return path. It actually serves 3 functions for that cable. Do not break the cable shield except where terminating in a shield environment. If you need to go to a motor disconnect, use a metal enclosure, steel enclosure. bond the sheath at both ends, coming into that enclosure and out of that enclosure. Cable shield should be connected to ground by a short pigtail. Now, this is typically done with our DriveRX VFD cable using our CoreFlex connectors with the ground bushing applied. All 3 bare bond conductors twisted together, taken through the ground bushing to bond the 3 bare bonds to the aluminum sheath, and that taken to protective earth or ground. We'll see more on that in a second. Use twisted pairs for communication cables to avoid crosstalk. When routing these power cables, these VFD cables, with any other control cables or power cables, separate them. Keep them separated. Now, for more guidance on all of this, even the separation of the cables, it's very important to look at the VFD manufacturer's instructions. They know the drives best. It's best off to follow their instructions. So on the left, you'll see what I was just talking about, how to terminate our DriveRX VFD cable. So the aluminum sheathed cable, where you're using a cable fitting body or CoreFlex connector connected to the armor of the cable, going into the enclosure, a ground bushing applied to the connector, and the 3 bare bonds twisted together and applied through that ground bushing and taken back to protective earth or ground. Likewise, for the flexible VFD cable solutions, you can use EMC sleeving, making sure to close up any openings not being used. So a very quick summary. We looked at VFD controls and motor speed, torque, and direction, resulting in improved system efficiency versus using a mechanical system. VFD applications we looked at very briefly, which focus on material processing and handling. Advantages being lower maintenance cost, increased productivity, and energy savings. A few of the complications that are mitigated by VFD cables, those being EMI, repetitive high voltage spikes, and corona discharge. Those are the key ones. And ultimately, bearing currents as a result of these. We looked at a few VFD cable designs and their key characteristics and installation tips.